Thank you, John, and thank you to the organizers for inviting me to speak here. So we've heard about some connections between random matrix theory and number theory, and I want to talk about a particular application to elliptic curves. So the new result that we'll get to right at the end is the work of Ian Cooper, who's my graduate student, who's sitting right here. I'm sure some of you have met him. So random matrix theory developed out of nuclear physics in the 1950s when it was used to model the excitation states of atomic nuclei. But we now know that we can use random matrix theory to shed some light on questions in number theory, and sometimes to make very precise conjectures for specific problems in number theory. So we're going to be talking about elliptic curves, and the reason that we can use random matrix theory to say something about elliptic curves is due to Katz and Sarnak. So as we've heard already this week, Katz and Sarnak say that if you take a family of L functions, so some naturally associated collection of L functions, each one of them will have a Riemann hypothesis, so it'll have zeros on a vertical line in the complex plane. And we're always going to normalize so that that critical line is at real part a half. And so Katz and Sarnak say that if you look at the statistics of the zeros low down near the point a half, then you can model them using the statistics of eigenvalues from one of these classical compact groups. And it depends on which family of L functions you've chosen, which one of these groups you end up looking at. So we're talking about elliptic curves, so it turns out that the group that we'll be interested in is the orthogonal group, so orthogonal matrices. And Katz and Sarnak also tell us that the word of warning is that we expect this connection between the statistics of the zeros and the statistics of eigenvalues in some appropriate asymptotic limit. So in your family of L functions, there's usually a parameter. It may be the number of L functions in the family, or it may be some parameter that orders the L functions in the family. And it's as that parameter goes to infinity that we expect to see the statistics of random matrices showing up. So that will be particularly important in this talk. So elliptic curves. We had an elliptic curve written on the board earlier this week. So it's some curve y squared equals a cubic in x. And to each elliptic curve is associated an L function. So written here is the Dirichlet series, where the Dirichlet coefficients an are determined by essentially counting points in a certain way on your points that satisfy the elliptic curve. But the point is, as far as we're concerned, for every elliptic curve, there is associated an L function. And we want a family of L functions so that we can talk about them in the sense that Katz and Sarnak describe. So we create a family of L functions in the following way. So this will be very familiar to many of you, but we'll go through it anyway. So the original L function associated with the elliptic curve E was just an over ns, n to the s. And so we twist the L functions by real quadratic characters, chi d, in order to get a new L function for each different value of d. So the characters for fundamental discriminants d, we have a character that looks like this. It's just given by the Kronecker symbol. So this takes values plus or minus 1 or 0. So for a given d, as you run through n's, you get a sequence of plus or minus 1s or 0, which sort of modify your original L function to give you a new L function. And then as you vary d, obviously you get a different sequence of plus or minus 1s and 0s. And so for each d, you get a different L function. And this L function is associated with another elliptic curve, which we maybe call ED. So again, we have that for each L function of this type, we have an elliptic curve. So we can talk about a family of elliptic curves or a family of L functions, and they're sort of the same thing. So, so we want a family. So this is the family defined here. So when you generate these L functions, some of them have an even functional equation. There's an even symmetry around the critical line where the complex zeros lie. And some of them have an odd functional equation. So the the impact of that on the zeros is the ones with even functional equation have zeros with an even symmetry around the point 1/2. So that is, they don't have to have a 0 at the point 1/2, but if they do, then it's a 0 of even order. So it's a second order 0 or fourth order 0. Whereas the ones with odd functional equation have an odd symmetry of the zeros around the point 1/2, and so they must have a 0 at the point 1/2, and it has order 1, 3, 5, or so forth. And in random matrix theory, you treat the ones with even functional equation and the ones with odd functional equation differently. You model them differently. And so here we'll just be looking at the ones with even functional equation. So we're taking L functions of this type with even functional equation, and we give ourselves some range in D. So this D, where, remember, D, for each D we have a different L function, and we take a range of D from 0 up to some cutoff X. So that's our family of L functions. And according to Katz and Sarnak, we have, they have orthogonal symmetry, and in particular, the zeros of these L functions near 1/2 are predicted to have statistics like the statistics of eigenvalues near 1 of matrices from SO2n. So SO2n, they're unitary matrices, they have eigenvalues on the unit circle, and they come in complex conjugate pairs. So they have a symmetry around the point 1, an even symmetry, which is the same as the symmetry of the zeros around the point 1/2. And so the point 1 in random matrix theory is sort of equivalent to the point 1/2 on the number theory side. Right, so we're expecting that zeros near the point 1/2 in this family will be modeled by the statistics of eigenvalues near 1 from SO2n, with the warning that this is in some asymptotic limit. So here the asymptotic parameter is x, that is the cutoff in D, or the number of L functions in our family, essentially. And it's in this limit that we'd expect to see this correspondence with random matrix statistics. So you might ask why. Why do we want to model the zeros of elliptic curve L functions with random matrix theory? And the reason, or one reason, is that associated to every elliptic curve is its rank. So the rank is a non-negative integer that describes the number of rational points on the curve. So that is the number of pairs x, y of rational numbers that satisfy that equation y squared equals the cubic in x. And the ranks of elliptic curves seem to be sort of elusive quantities. There are a lot of things that aren't known about them. So I think I read that in 1901, Poincaré asked in a natural family of L functions like this, associated with elliptic curves, what's the range of ranks that you might find? And so that's a question that's been around for over 100 years that we still don't know the answer to. As far as I know, we don't even know if ranks are bounded within a family like this, or if they could be arbitrarily large. So there are questions to be answered here. There's the recent work of Bhargava and Shankar, where they have a bound on the average rank in a family of curves like this. And this is a monumental result, but it's still a long way from sort of understanding the distribution of ranks, how many curves have rank 0, how many have rank 1 and 2 and 3 and so forth. So the question is whether random matrix theory can give us some kind of a hint about how ranks are distributed in families of elliptic curves. And the reason why this might be possible is thanks to the Birch and Schwinert and Dyer conjecture, which relates ranks of elliptic curves to zeros of the associated L function. So the statement is that the order of the zero of the L function, the kind we've been talking about, at s equals 1/2, so that is at the critical point, is equal to the rank of the associated elliptic curve. Okay, so it associates the rank to the order of that zero at the point 1/2. And in particular, the L function at 1/2 is 0 only if the elliptic curve has infinitely many rational points, which means the rank is greater than 0. Okay, so by counting the number of L functions which are 0 at the point 1/2, we can count the number of curves in the family that have rank greater than 0. Okay, and random matrix theory, through the eigenvalue statistics, tells us something about zero statistics of these L functions. So the hope is that maybe we could use that connection to say something about the distribution of ranks. So that's why we want to understand or be able to model the zero statistics of these elliptic curve L functions. And we know quite a lot about the zero statistics. So here's a picture of the one-level density. So just to go through what this is. So we have a family of L functions. So we're twisting E11 with D's between 0 and 40,000. So we have a whole bunch of different L functions. Each one has a picture that looks like this, so a Riemann hypothesis. And what this graph here is, it just says for every L function in your family, you take this picture and collect the heights of all of these zeros between a half and whatever. We go up to 30. So all the zeros up to 30 of every L function in your family. So you just pool those into one great big data set and plot a histogram. Okay, so we've collected all zeros up to 30 of all the L functions with D between 0 and 40,000 and plotted a histogram, we get this. So a peak in this histogram will mean that this is a height on the critical line where it's quite likely that you'll find a 0 as you kind of trot through your family. And a trough in this picture means it's a height on the critical line where you are less likely to find a 0 as you trot through your family. Okay, so hopefully that explains what the solid curve is on this picture. So the dashed curve is a prediction for the one-level density in this family. And I'm not going to say a lot about how it comes about. We heard in Brian's talk that there are conjectures for moments and ratios of L functions, and that the conjectures for ratios of L functions contain information about the statistics of zeros. And so that's the formula for this prediction here comes via these ratios conjectures. So I won't say anything else except that we have a formula that really beautifully captures all these dips and peaks, and we can completely understand where they all come from. It's a formula. You can look at it and you can see, you can explain why this is high and low at various places. The formula is sort of a combination of random matrix theory and number theory. So at the origin, you get these kind of gentle oscillations, which is basically following the random matrix statistics. So this is for short-range correlations here. Sorry, for low heights here. And, but as we go to higher heights on the critical line, number theory takes over, and we get this more kind of, I don't know, random-looking fluctuation. Okay, so it's a combination of random matrix theory, a kind of random matrix theory structure with number theory details on top. But anyway, but the point is that it looks as though we kind of understand these zero statistics because we can predict exactly what they look like. But the thing that you don't see by looking at the picture like this is what is happening at the very beginning here. So now I'm going to show the same picture, but just zoomed in right at the origin. Okay, so this is the same picture. We see the nice kind of gentle oscillations, which are sort of come from random matrix theory. And this is exactly the same as before. So this is a histogram of all the zeros of all the L functions in the family up to whatever height this is now, around 0.6. And again, the ratios prediction is the solid, is the smooth curve. And so we can see that, that there's a problem right near the origin here, in that the data is showing us that if we look very close to the point of half, we're unlikely to find zeros of these L functions. So we call this repulsion from the point of half. The zeros don't like to get very close to the point of half. But the ratios conjecture prediction doesn't capture this at all. So, so this phenomenon was first spotted by Stephen J. Miller. So he did an experiment. He was using a different family of elliptic curve L functions, but you don't need to worry about that. The phenomenon is exactly the same. So here he's plotted, it's sort of like part of the one-level density. So he's taken just the first zero. So again, he has a family of elliptic curve L functions. He's got 750 of them. For each of the 750 L functions, he takes the height of that first zero above the point of half, and he makes a histogram of the heights of those first zeros and gets a picture like this. So this is essentially like the first hump in this picture of the one-level density, right? Because this was all the zeros. But the first peak here will be the lowest zeros. So essentially, Steve is plotting just the first hump here. Okay, so he gets a picture like this. We see the repulsion from the point of half that we saw on the one-level density. So Steve is picking out just the rank 0 curves. So remember we said the L functions that have a 0 at the point 1/2 correspond to the higher rank curves, so that have rank higher than 0. So Steve has just picked out the ones that have rank 0. So those are the ones that don't have a 0 right at the point 1/2. So this picture is slightly misleading in that there is actually a large spike at the origin, which corresponds to the zeros of the higher rank curves, but it distorts the picture too much if you put it in. So it isn't plotted, but there is this is curves of all L functions associated with curves of all ranks, and so there is a spike of zeros at the origin, but Steve is just looking at the curves which have rank 0. So this honestly is their first, the first 0. It's the one up here. So we see in his picture the repulsion that we saw before. And then we think back to Katz and Sarnak, and Katz and Sarnak tell us that the statistics of the zeros of these functions should be predicted by the statistics of eigenvalues from SO2n. So Steve drew a picture in his paper of the distribution of the first eigenvalue from SO2n matrices. So they have their eigenvalues on the unit circle. You remember the point 1 was the symmetry point because the eigenvalues come in complex conjugate pairs. So the point 1 is like the point 1/2. And so the equivalent thing to look at when you're talking about the lowest 0, the 0 nearest to 1/2, is the eigenvalue nearest to 1. Okay, so here we've generated lots of matrices from, in this case, SO4. I looked at the eigenvalue closest to 1 and plotted a histogram of the positions. And we can see there is no repulsion, and this is true. It's not because we picked a certain size of matrix. Whatever you do, you won't find repulsion at the origin for matrices from SO2n.
Do the eigenvalues come in complex conjugate pairs?
Yes. Yeah, sorry, my picture isn't very accurate, but they're supposed to be in complex conjugate pairs. Yes. So it's not that we doubt Katz and Sarnak, right? Katz and Sarnak said we expect this correspondence to happen in the limit as some natural parameter goes to infinity. And Steve actually has evidence. He plotted a similar plot for a slightly higher parameter range, and you can see this gap closes as your parameter goes to infinity. So we're not doubting Katz and Sarnak. We believe that as the appropriate parameter goes to infinity, the gap will close and eventually will be small enough that on whatever scale you look at it, it'll look pretty much like that picture. But the point is for the amount of data that we can calculate, the picture looks like this one and not this one. And so we want a model that predicts the correct distribution when you're not in the asymptotic limit, when you have finite parameter value. So that's the goal. The question now, I guess, is why do we see this repulsion in the zeros of elliptic curve L functions? We think it's because the L values at 1/2 are discretized. So there was a lot of work which culminated in a formula by Konen and Zagier, which looks like this. So these are the L functions we're looking at, right? The quadratic twists of an elliptic curve L function. We're looking at the value at the point 1/2, and they give a formula for this value, which is a constant, and then this CED squared, let's just call it C squared, where C is an integer. And then over root D. So the point is that C could be 0, in which case the L value at 1/2 will be 0, or the next smallest value that C could take is 1, right? So the L value is either 0 or it's kind of bounded below by kappa over root D. Okay, so there's this discretization. It's like a gap, right? It can be 0 or it has to be bigger than some value. And you can imagine that this might cause repulsion at the first 0, right? Because if the value at the point 1/2 has to have a certain height, then unless you have a really steep derivative, it means your first 0 is likely to be not too close to the point 1/2. So it makes sense that this might be the explanation for why we see the repulsion of zeros from the point 1/2. So another way of saying this, which might be useful to what I say later, is that if the L function is less than this lowest non-zero value, kappa over root D, then it's 0. Not just another way of saying the same thing. The hypothesis of Dueñas, Wen, Keating, Miller, and myself is that this discretization is what causes the repulsion of zeros from the symmetry point, from the point of half, and that the resolution would be to similarly discretize the values of the characteristic polynomials. So the characteristic polynomial of matrices in SO2n looks like this. So here are the eigenvalues, e to the I theta j and e to the minus I theta j. These are the complex conjugate pairs of eigenvalues. And the characteristic polynomial is a function that goes to 0 at each of the eigenvalues. So when S takes the value of the eigenvalues. There's lots of evidence to suggest that values of characteristic polynomials are a good model for values of L functions. So we've already heard that the zeros of the characteristic polynomials, which are the eigenvalues of the random matrices, show statistics like the statistics of zeros of L functions. But there's also evidence that the values of the characteristic polynomial model the values of the L function. So we've heard probably from various people about this, that using moments or average values of the characteristic polynomial, you can predict moments or average values of zeta or L functions. But I've got a picture to convince you that the characteristic polynomials are a sensible model for the values of the L functions. So what we have here is distribution of values of, again, we're taking twists of E11. We're looking at the values at the point a half. We're taking D between 0 and 400,000. So this is our family. And now we're looking at values rather than zeros. So don't get confused. There are two kinds of plots we'll be looking at. One is distribution of zeros. One is distribution of values. So this is distribution of values. So we take all these L functions, right, with D between 0 and 400,000. For each one, we calculate the value of the L function at the point a half and just make a histogram of those values. And that's the kind of stripy plot. And it's being compared with the distribution of values of characteristic polynomials at the point 1. So that's the equivalent symmetry point. And we're looking at SO24, and you know what size of n to take by essentially equating the density of zeros near the point a half of your L function with the density of eigenvalues. So that gives you a kind of equivalence between n and x. So for this value of x, it turns out that the value of n to use is 24. Well, no, the value of 2n to use is 24. So the other plot, the kind of smooth plot, which lies on top, is you generate lots of matrices from SO24, you calculate the value of the characteristic polynomial at 1, and you plot a histogram of those, and you get the smooth curve here. And so I think it's reasonable to say that the distribution of the characteristic polynomials is a reasonable smooth approximation to the rather choppy distribution of the L values. So remember, we had the formula for the L values. It was some constant, an integer squared over root d. So again, this plot is sort of missing the big spike at the origin where the L functions that have value 0. But then we see there's a kind of peak which belongs to L functions that have the value of c taking the value 1, and then a little dip, and then there's a peak that corresponds to the values of c that are taking the value 2, and so forth. And so it has a kind of bumpy distribution, but the characteristic polynomial sort of is some kind of smooth approximation to that. So we can feel at least mildly convinced that the characteristic polynomials are somehow modeling, in some smooth sense, the distribution of the values of the L functions. And so what we're trying to get is we're trying to get a model for the statistics of the zeros of these L functions. And our test for how good a model is going to be when our model is going to be some set of matrices. So here we have the set SO2n. And so we take a set of matrices and we look at the distribution of the first eigenvalue of that set of matrices, and we see how close the distribution of that eigenvalue is to the distribution of the first 0 of our family. And the closer those two distributions are, the distribution of the first eigenvalue with the distribution of the first 0, the better we're going to say our model is. So that's going to be the measure of how good our model is how well it predicts that distribution of the first 0. So if our model were the whole of SO24, then we would look at the distribution of the first eigenvalue for all matrices in SO24 and compare that with the distribution of first zeros. So this is the cumulative version of the plot that Steve Miller had. So he had a plot that looked like, that showed the repulsion and then had a hump. So this is just the integrated version of that density, or the cumulative density. So the crosses is the cumulative density of the first zero nearest to a half. For L functions, we're looking just at the rank 0 curves, versus the solid line is similarly the cumulative distribution of the first eigenvalues, the ones nearest to 1, of matrices from SO24. So so the cumulative plot just tells you, if you look right here, the height of the plot here tells you essentially what proportion of your L functions have a 0 below this height here, say 0.4. Right, and so the test of our model is going to be how well these two curves match each other. And this isn't doing a particularly good job because you can see daylight between these two curves. So the whole group SO24 isn't a particularly good model for the statistics of the zeros, as we already know, because it doesn't capture that repulsion at the origin. But the proposal is that the way to get a better model is to sort of copy this discretization formula, but on the random matrix side. So let's take a matrix from SO2n. Its characteristic polynomial, we said, looks like this. And so we want to take the value of that characteristic polynomial at the point 1 and do essentially what this formula says. This formula says the L value can either be 0 or it's bigger than some non-zero value. So we want to do the same thing to get the rank 0 curves. We want to be looking at the L functions that are bigger than that non-zero value. So to model rank 0 L functions associated to rank 0 curves, we're going to generate matrices from SO2n, and we're going to jettison any of them that have a value of the characteristic polynomial at 1 that's too small, and just keep the ones that have a value of the characteristic polynomial at 1 that is bigger than some cutoff. And this we called the excised random matrix model because you're excising the matrices with too small a characteristic polynomial at 1. Right, so this is the model, and the obvious question is, what value do you take for this cutoff C, right? What value do you choose to tell you how many of your matrices to retain? Okay, so let's go back to the distribution of values. So this is the same picture we saw before, so the distribution of values of the L functions at a half versus the distribution of values of the whole of SO24, where we're looking at the value of the characteristic polynomial at 1. And this picture up here is the same thing zoomed in at the origin. So, and this shows the gap, which you can't see on this picture, but the gap, which is created by this formula. So the L functions with value 0 aren't on this plot, but because they distort the scale by being too big. But if we put them on there, we'd have a great big spike here. Then we'd have the gap that we can see there, and then this would be the L functions with a C equals 1 in this formula, so they'd do something like this. And if we extended the zoomed in plot a bit more, then we'd start to see the peak for the values where C equals 2, and so forth. Okay, so the picture really looks something like that. Remember, we're trying to choose a natural cutoff where we say we'll keep the characteristic polynomials that have value at 1 bigger than such and such. And so you look at these two pictures, and sort of the obvious thing to choose is to say, well, I'm going to choose the characteristic polynomials with value bigger than this point here, because we're trying to model these values of the L functions. And then what we'd be saying is that the characteristic polynomials with value greater than this cutoff, those will be the model for the statistics of the zeros of L functions associated with rank 0 curves. And so then you naturally ask, well, what about the matrices you've discarded, right? The ones with characteristic polynomial less than your cutoff value. And the idea is that they maybe can predict the number of L functions which have rank greater than 0, right? So if these guys are predicting the ones with rank 0, then maybe these guys are predicting the ones with rank greater than 0. So the random matrix plot, I don't know, somehow comes through the middle like this, right? The smooth plot on there. And so in some sense, the idea is that the sort of the mass in here is going to, in some way, give us a prediction for the number of L functions with rank greater than 0. So we're looking at just even L functions with even functional equations, so they have even rank. So we're looking at curves of rank 2, 4, 6, and so forth. So the people who know this work well, my collaborators in the audience, are probably fidgeting at this point because I'm glossing over some details which are interesting and important, but in order to give you kind of a clean picture, I'm not going to mention them. So I will try and say things that are accurate, but hide some of the details. Anyway, so the next step is to take the sort of look at the mass in this, under this purple curve under here and try and predict the number of curves in the family that have rank higher than 0. Okay, so this is a conjecture of Connery, Keating, Rubinstein, and myself. All of us are in this room here. And so what we essentially did was we said we're going to count the number of L functions in our family. So here the D has turned into a P and is now restricted to primes for reasons that I won't go into, but it's essentially the same family. So we've got D or P up to some cutoff T. We're counting the L functions that are 0 at the point of half over sort of all the L functions in the family. So we're looking at the proportion of L functions in the family that have a 0 at the point of half on this side. And on this side, we get a prediction which comes by using the shape of this purple curve, so the random matrix theory curve here, in this region on this side of the cutoff. The shape of that curve gives you this prediction on this side. So it says that the proportion of these curves is like t to the minus a quarter log t to the 3/8. And there are other methods which don't involve random matrix theory for predicting the t to the quarter, but I think there's no other method besides random matrix theory and using the very detailed knowledge of the shape of that purple curve. I think there's no other way than that to get the power on log t. So random matrix theory is kind of vital to this conjecture. And Mike's done, like Mike Rubinstein's done lots of numerics to test this conjecture, and his numerics are very convincing that the growth with t, so the power of t and the power of log t, is, as far as we can tell, correctly predicted by this conjecture. And why are we interested in this quantity? Well, of course, it's because Birch and Schwinert and Dyer tell us that by counting the L functions that are 0 at the point of half, we're counting the number of curves in the family that have rank greater than 0. So essentially counting the curves of rank 2 or higher in this family. So that looks very nice. We seem to have captured the correct growth in t, but, and there is a but, the coefficient here is wrong. So when you choose this cutoff and you use this shape of this purple curve in here to make this prediction, you get the wrong constant. Yeah. And there's sort of nothing you can do to fix it. You try whatever you can, and it just doesn't work. So, so this prediction came from choosing the cutoff, which is essentially right there where the smallest value of your L function is. So this, remember, we have D between 0 and x. And with this formula over here, that means this point is going to be kappa E over root x, right? Because x is the largest D, and so it's going to give you the smallest value when you plug it into that formula. Okay, so by using that cutoff, we get the wrong constant in this formula here. But so what if we go back to this picture and we say, well, let's allow ourselves to choose a different cutoff, right? Let's not take the sort of obvious one, but let's see what happens if we vary the cutoff. Let's try lots of different cutoffs. So take in SO2n, choosing lots of different places to cut off the matrices that we keep and the ones that we discard. So then you get a picture that looks like this. So here, cutoff is along this axis here. So it's experimentally, you generate your matrices from SO2n and you test retaining the ones with the characteristic polynomial at 1 bigger than a cutoff, and you vary, do lots of tests with different cutoffs. On the y-axis is a measure of how good the model is, and we said that our measure for how good the model is going to be how well the distribution of the first eigenvalue in the set of matrices that we've retained models the distribution of the first 0 of the family of L functions. And so this is some measure, which I won't go into the details of, but it's a measure of the error between the two models. Okay, so when it's minimized, it means we've got a good model, and when it's high, it means there's a lot of daylight between the two curves. So we can see there is a minimum. So that is, there's a kind of optimal cutoff on this picture to choose, where if we keep the matrices with just a characteristic polynomial at 1 bigger than that cutoff, that sort of optimizes the model. And if you want a picture of that to compare with when we took all of SO2n, the picture's here. So again, this is the cumulative density of the first zeros versus the cumulative density of the first eigenvalues, where we've excised SO2n using the optimal cutoff, so the one at the minimum here. Okay, and we see now we get a pretty good fit, right? You remember before when we used all of SO2n that you could see kind of space between the two curves, whereas now, as far as you can tell by eye, you have a fairly reasonable fit between the two curves. So, but then the next interesting thing is that I have drawn a dotted line here, and it looks as though I've drawn it at the minimum of the curve. And happily, it is pretty much the minimum of the curve, but that's not why I drew it there. So the dotted line is the cutoff in here that you would take if you wanted this area to predict the correct coefficient in this formula here. So kind of working backwards, Mike tells me how many L functions there actually are that are 0. Working backwards, you can figure out what cutoff should I have taken in order to get the correct constant here. And it turns out that cutoff is at this line here. So it tells us that we have a consistent model, right? Because it says the matrices with characteristic polynomial bigger than some cutoff, they are a very nice model for the statistics of zeros of L functions associated with rank 0 curves. Whereas the sort of the number or proportion of characteristic polynomials with value at 1 less than that cutoff gives you the correct number of higher rank curves. Okay, so I think we can conclude that it's a good model. It does what we want it to do, and it's consistent. But whenever I talk about this, there are at least 2 questions that always come up. So the first one is one that always bothered me, which is that the optimal value of the cutoff in the excised model is much smaller than this kind of obvious cutoff, right? So initially we said we'll take the cutoff to be here, where we have the smallest L value, but that isn't the value that works, right? That one doesn't work, and the one that works is somewhere over here. And so the question is why, right? Why is it sitting in the middle of the gap there? And the other question that always gets asked, I mean, literally every time I've given this talk, so I know one of you is sitting there with this question in your head right now. The other question that everyone always asks is, okay, this formula here, it tells you there's a gap, but it also tells you more. It tells you about a structure out here with these kind of peaks, and we've, in the excised model, we've captured the gap, but we haven't captured any of the further structure. Right? So someone always says to me, have you thought about trying to capture the rest of the structure sort of from the other peaks in the formula? Thanks to Ian, who's done work on this, I can now say something about those 2 questions. So, right. So this is the picture that you get with just the excised model using kind of the optimal cutoff here. As we say, it's a bit lower than where you see the lowest L value, but that's the one that gives you the best model. But then what Ian did was he cunningly created a random matrix model which exactly fits this first peak. Okay, so he does this by, he generates random matrices, and if they have a characteristic polynomial at 1 with a value out here, then he keeps them. If they have a characteristic polynomial with a value in here, he discards them. But if they have a characteristic polynomial with a value in here, then he keeps them and discards them with a certain probability, which is given by the height of the curve, essentially. And because he's very cunning, you can see he can fit the peak even where it goes, sort of where the probability goes above 1, as it were, by allowing himself to keep multiple copies of a matrix. But the point is that he actually has a set of matrices, right? So he really and truly has a set of matrices which have characteristic polynomials at 1, which have this, this distribution of values. So the first peak is just set to match the peak in the number theory data, and the rest of it is just Haar measure. And this provides an even better model for the statistics of the zeros. It's not a model that you'd really advocate anyone to use because it involves actually, having to know the shape of the number theory data and then kind of rigging your matrix model to fit that shape. Yes?
Just clarify, I mean, if you're selected, you can make it fit anything. So, like, what exactly are you, how's the selection being done? You said you fit the first peak, but what else are you selecting for? What's...
I'm not quite sure what you're asking.
You compute you have this characteristic polynomials, and you're trying to use them as a model for this L data. So if you were to pick and choose them with the same histogram, you'd get the exact same shape. So that's not what you're doing.
Well, so you haven't. Well, you should wait for the punchline, right? So the point he has chosen it so that they exactly fit the shape. Okay, so that's what we're saying. It's not a model in the sense that you're using the data, the number theory data, in order to create it. So it's not a model that you'd ever want to use. But just wait. Can you wait one more slide, and then you can ask me if you still have questions. Okay, so the point is that he's cunningly got himself a set of matrices which have a distribution of values which fits perfectly the first peak and then is Haar measure from then on. And as Mike says, that isn't a terribly interesting thing in itself, but what we have here is the cumulative distribution of the excise model, and we call this the modified weight model. So if we go back to the excise model, I'm going to show you the cumulative distribution of this gray, smooth gray curve here. So it's 0 for a little bit at the origin. You can't really see that because the bin size is too big, but there's it's the stripy plot here. So it has a gap at the origin which we can't see, and then it starts to gain some mass and sort of smoothly goes on from there. So this is a cumulative plot, like summing up all the bins on the density plot. And that the excise model gives you the stripy bars. And now we do the same thing for the modified weight model. So that's this one here. So we, again, cumulative plot of this. So it starts a bit later than the excise model, right? Because the excise model kind of kicked in earlier. So on this plot, we see the first bin in the modified weight model having some mass here. But then it kind of catches up because it's got this like super enormous peak. So a whole bunch of mass comes in all at once. And we see that here, and so forth. But the interesting thing is that these two plots match after this point here, where the second excision is. So this is the point for kappa over root x, right, where the peak with the c equals 2's kick in. And so the reason that that's interesting is that it explains why the cutoff for the excise model is here. And the reason it's there is because putting it there gives you the correct mass in your model. The same mass as this first peak. So it doesn't have the same shape as the first peak, but the total mass in here, between here and here, is the same as if you had mass in the shape of the number theory peak. So I think it explains why the cutoff in the excise model is where it is. And it sort of answers the second question, which is, does it help to, to model further these further discretization points? And I think, so I think the point is you could consider modeling further out, but it seems that the most important thing for a model is that you get the correct mass at the beginning of this distribution in your model. So so the point of Ian's modified weight model is that it's not a model that you'd want to use to model L functions, but it explains some of the questions we had about the X-size model. Okay, so that's the X-size model and beyond. Thanks.
All right, well,